My name is Ye. Today, I'd like to talk about the Halo optimization. And if we have more time, we can quickly go through the proving process so that everyone can have a sense of how to generate proof from those circuits. So this is the outline for today. So there will be three parts. Firstly, I will quickly introduce a high level, like how you are generating proof for a program. And the second, I will focusing on this Halo optimization, like how you are writing constraints for program and what kind of toolings you can use in your circuit, with some examples. And finally, if we have some time, I will quickly go through this prover, how you convert this constraint to polynomials, and finally commit and open for verifier to verify that. Okay, so let's start with a high-level intro. So the idea of the proof is that you want to generate very sustainable proof for any program. So I take an arbitrary computational program here, written in. The idea of the proof is that you want to generate very small proof for any computational program. For example, I take an arbitrary program here, written in high-level language, and you want to use a proof saying that this program executes correctly. And for our case, we want to prove that, use one proof to prove that every execution step for EVM is correct. So this computation or this program can be like arbitrary type. And how you are going to do that is that you firstly need to represent your program, re-implement this program using something like intuitively some ZK language, where you re-implement your program, which initially it might be in any high-level language. This step is called circuit arithmetization. You basically need to write a bunch of mathematical constraints, and using those assertions, like for example, this is a very simple example saying that x times x equal to variable 1, and all those like math assertions. And using those assertions, you can prove that this program is correct if you have a valid assignment for those constraints. So this is the most important step, especially for auditors. Basically, auditors need to be careful that when you are writing those constraints, it's equivalent to the initial program. You are not missing any constraints. You are not missing any information. And then after you get this circuit, those constraints, you run some proving algorithm, and which is you use this prover, Halo 2 prover, to generate the proof. So there are two separate things. One is on the front end, where you use the circuit optimization to represent your program, and on the back end, you use some proving algorithm for generating the proof. And now let's dive into like the Halo optimization. So to start with, I know like many auditors have experience auditing some R1CS circuits, especially written in Circom. So I take a very like many random pieces from some Circom code. So basically you can, like in Circom or in R1CS, you can write some constraints like this. You can multiply two linear combinations and assign or connect that to a different value or wire. So it's not that all the constraints in Circom or R1CS is degree 2. So you can only allow one multiplication in each constraint, like either it's here, this A poly come from some linear combination from variables, and all those, like this bracket, you have multiple like variables here. So R1CS and Circom has this format of degree 2 constraints. But on each side is a linear combination. And in general, like in R1CS, you have all those n variables. And for each constraint, like each row of constraint, you can write arbitrary combination for those variables times arbitrary combination for those variables equal to some combination for variables. So either look like this or this, but only, so one constraint can only contain one custom gate. And after defining those constraints for a program, your statement will be, I know a concrete assignment for those witness, like input, VA, VB, and VC, that satisfies all those constraints. If prover can prove this, then like it can prove that this program can execute correctly to get the output you want. So this is like, we start with Circom and R1CS. And for Plonkish optimization, it's actually quite different. So you are not layouting all your variables and all the intermediate values in a vector, but instead you use a table. So you can configure this table to have, like, for example, like this has multiple columns, and we divide that into witness and some table column. And then you can put all your values like you use during this computing this program here, like you can put your input here, and you So sorry, I'm in quarantine hotel, so the network is pretty bad.
Do you want me to? About it.
Sorry.
If you want me to do the presentation, maybe while you're fixing, I'm okay. Just let me know.
Okay. Maybe I can still try, and I switch to my hotspot. So
let's try again. Okay.
Yeah, I can. Okay. Yeah. Okay. Is this the last slide where I missed or? Okay. Yeah. I turn off my video and try. So is this the last slide which I talked
Yes.
about? I don't know
Yes.
where. Okay. Yeah. So in Splunk organization, differently, you are not layouting all your witness in vector, but you can configure like how many columns you are using for this table. You can configure, like, for example, this is like 5 columns and some table columns, and then you can put all your like input, output, and some intermediate values in this table, and then you can define something called custom gate, which is not limited to the form of this R1CS, which is linear combination times linear combination, but you can define something which is more customized. For example, you can define any shape, like you can define this very regular shape, and you can define the relationship for the variables within this shape, like V3 times VB3 times VC3 minus VB4 equal to 0. So using this custom gate, you get 2 benefits. One is that you can represent some higher degree constraints. So for example, like this is, you can include 2 multiplications in 1 constraint, but in R1CS, you can only include 1. So it's also more customized because, for example, if your program use some pattern frequently, and then you can abstract this pattern and represent this using some custom gate, and you can get some more customized for your program. It's not only limited to this this linear combination form. And more specifically, when we are defining a custom gate, we're actually defining a shape for this custom gate, but we didn't specify which specific position it is. For example, if you want to constrain V3, VB3, VC3, and VB4 at this specific position, then we need to multiply with another like value called selector, which the other values will be 0 and only like be 1 and or be turned on at a certain position. But for simplicity, I just write this V3, VB3 at the custom gate. But basically, when you are defining the custom gate, you are defining a shape, and this shape can be reused across the whole column. For example, if you select it to be open at this place, it can be reused. The same shape can be applied to the whole table. So this is how you define custom gate. And you can define random shape, as I mentioned, like you can define this shape, or you can define very regular shape like this. So this is a flexibility that Halo 2 can give you when you're writing your program. And another thing you can also use is called permutation, because as I mentioned, like you can define multiple gates, and but those gates are still independent. You can connect the output for one gate to the input of the other gate by making this cell to be equal. So for example, you can define a sequence of value that they are equal, like VB4 equal to VC6 equal to VB6 equal to V6. And so this is something called permutation. This is another arithmetization you can use in for this Splunkish arithmetization. And to give you an example like how you are using this custom gate and permutation in practice, let's take a look at some Fibonacci example. So you can configure your table to be 4 column, and then you fill up all the witness values, like your 1, 1, 2, and 1, 2, 3 here, 2 plus 3 equal to 5 here, 3 plus 5 equal to 8 here, and you can like fill up all this table. And the relationship you need to prove is that for each row, the value in the first column plus the value in the second column equal to the value in the third column. So you can have some customized relationship like this, and it can be reused for all those rows. And besides that, you also need to prove that this 1 and 2 is the input for the next gate. So you need to prove for some permutation relationship for the first and second row, for a second and third row, and you can define some permutation relationship. So this example demonstrates like how you are using this custom gate and permutation in practice. And Haicheng will introduce more how you implement this program in Halo 2 in the next session. And besides the custom gate and the permutation, another thing you can also use for Plonkish arithmetization is called Lookup. So this lookup is some membership relationship where you can define a tuple, which is like V7, VB7, VC7, this is a tuple, and you can prove that it belongs to a table. So what does that mean? And why is this useful is that I can give you an example. So for example, if you want to prove that VC7 belongs to the range between 0 to 15, right? In R1CS, what you use to do is that you can decompose this VC7 to like 4 bit, and you prove that those 4 bit are actually bit, which is like you use 4 constraints to constrain that it's either 0 or either 1, and then you can linear combine those values using this binary format to get VC7 to prove that VC7 can be represented in this form, and it's all bits, so it's within this range. But with this lookup argument, you just need to use 1 constraint, which you prove that VC7 belongs to this table column, and this table column will iterate from 0, 0, 0, 0 to the 15. And you just need to prove that if this belongs to this table, then it's definitely within this range. And similarly, for a tuple, you can prove that if you want to prove that V7 XOR VB7 equal to VC7, instead of decomposing all the variables into bit and doing bitwise operations, you can instead have a like fixed table, preprocessed table, storing all the possible relationships for XOR, and prove that this tuple belongs to this table, and that's it. And this is also especially very important in our zkEVM circuits, because you can also use this lookup to do some verifiable RAM operation, because it's a virtual machine. So every time you need to like write to your memory stack or storage, so you can put that into a table row, and then like next time when you're reading from the same row, then you just prove that it belongs to this table, this RAM table, and that's it. And Haicheng can introduce more in the zkEVM session, but this is very important when you're writing the zkEVM circuits. And now just a quick summary, like for Plonkish arithmetization, you can write 3 different type of constraints. One is custom gate, where you define some shape, and then you define the relationship for this gate within this gate, like something like this or this or this. And you can define permutation, which will link those gates together. It's basically a sequence of field equation, like VB4 equal to VC6 and something like this. And also you can define some lookup arguments. For example, this tuple belongs to this table column. And even more flexible, like you can define something even more flexible than this V7, VB7, VC7, is that in Halo 2, each element in this tuple can be some expression. So by saying expression, I mean, so instead of putting like V7 here, you can maybe put like V4 plus VB4 plus VC4 as one element in this tuple. And so by saying expression, I mean, it's an expression of the variables in this table, and as your elements. And you can look up this expression tuple and whether it belongs to a table or not. So those are like 3 different constraints you can write in Halo 2 circuit. So any questions here?
So why do you have table 1 and table 2? I mean, why the columns are combined into 2 tables? Because from your description, it looks like that each column is separate thing. I mean, what is table here? Yeah. Table 1 and table 2.
Yeah. So for example, like table 1 can be proof for XOR operation. So you can iterate all the possible XOR entries like in table 1. And for example, in table 2, you can prepare some other logic, like you can put some like range or storage table. So it's just different table columns are used for different functionalities, and so it's different areas, right? So you can't put like when you're proving for range, you approve for XOR, it's definitely need different like functionalities for tables, right? So that's why like I mentioned, like it's different columns.
Okay, do all the columns have to have the same height?
Yeah, that's a good question. So within one circuit, it need to have the same height. You can pad the same elements like in the for the same as the last element and here. Yeah, but and also maybe you can like stack different tables together just with some different index to distinguish different tables. So there are some way to compress different tables, but in a circuit, usually like the tables are the same length. Does that answer a question or any more questions?
How would you compress these? Because you say you can, they all have the same height, and you're saying compress, but how do you do that?
Oh, yeah. So if you are not doing like you are not stacking two tables together, then you just pad to the same height and that's it. But I mean, like if like two tables are very short, you can just put them in the same column and then add another column like as index for different tables. But that's just optimization for on the prover side and how you are like optimizing the, like for example, if this table 1 only have three rows, table 2 only have 5 rows, but your circuit has maybe like 2 powers 18 rows, then you can definitely put the two tables together and stack in the same column and then add another extra column to use as index to distinguish different table, if that makes sense. That's an optimization. That's not something like you are doing automatically.
Yeah, thanks.
Okay. Any more questions or? Okay. Yeah. So those are the optimizations you can use for Halo 2. Basically, it's custom gate, lookup, and permutation. And finally, we can go through this like Halo 2 prover and the whole proving process very, very quickly. So when you are writing a custom gate, as I mentioned, like so for example, you want to constrain that V5 times VB5 times VC5 minus VB6 equal to 0. You are not like when you write out those constraints, and on the backhand side, you will result in a polynomial. So each of those custom gates will result in a polynomial. And those polynomials define relationship between columns. For example, if V5 belongs to this column, then like this column is A1 column. So you can interpret all the values in A1 column and get this like column polynomial called A1x. And they say A2x, they say A3x, you can get a polynomial for all the columns. And then when you are writing out those constraints, you are actually constraining that A1x times A2x times A3x minus A2 like omega x. So because like VB6 is on the next row. So when you are accessing the next row, or you are using something called rotation in Halo 2, and which on the back end will transfer to this omega x. So if you want to access VB7, it will be like A2 omega square x. So this is like on the back end what's happening. So, but from this polynomial, you can see that it doesn't specify that it's V5, AB5, VC5, VB6. It can be arbitrary, like height, arbitrary position, but just you need to keep the shape to be the same. So if you want to specify this specific area, as I mentioned, you need to multiply with some selector, which is all 0, but only open here. And then after multiplying this selector polynomial, you can get your constraints. So this selector polynomial will tell you that if x belong to those rows, it's 0. So you don't need to constrain this relationship. But if it's 1, then like on this specific row, this custom gate will function. So this is how like from each custom gate, you will result in a different polynomial. And for different rotations, you will have this like omega x, omega square x, or different rotations. And you can reuse the same shape of custom gate across all the many different rows. For example, you can open at this place, and this place at the same time. So this is how you like what's happening on the custom gate. Like for in short, for each custom gate, it will result in one unique polynomial. And for lookup, without going into too much detail, it's also this belonging relationship will convert to some polynomial identity relationships. So, but different from custom gate, it will generate like four different polynomial constraints, like this is Lagrange polynomial, and this is like some zx, it's because for custom gate you are only defining over columns, over the cells in this table. So all the polynomials you need here are from your table column. But for lookup, the argument that using Halo 2 will introduce some other additional polynomial, this a prime x, t prime x, and dx. So you need to compute like 3 different polynomials for your lookup arguments, and also generate 4 different polynomial constraints. So this is for this tuple relationship. And also, as I mentioned, like you can define even more flexible relationship. You can replace all the values in this tuple with some expression. And similarly, you also use like 4 different polynomial identities to constrain this like belonging relationship. So this is just high level intuition is that for each lookup constraint, it will be converted into 4 polynomials. And for this permutation relationship, the only thing that matters is how many columns is involved in this permutation. Like for example, so those are 3 different cells, like V0 equal to VB1 equal to VC3, and it involves 3 columns. And for V5 equal to VB5, it also involves like the same 2 columns. So the permutation only matters for like like where your cell is and how many columns it involves. So for example, like for this area, it will only involve those first 3 permutation columns. So you can generate like you only need to use 2 polynomial constraints to constrain this relationship. So as far as you can define arbitrary permutation relationship as far as they are within the first 3 columns, and you can have multiple like permutation arguments for different columns. And so from high level, each permutation relationship will convert to like 2 constraints, polynomial constraints. So at the end of the day, after expressing your program using this custom gate, like lookup and permutation, you will result in a bunch of polynomial identities. So each is just some polynomial times polynomial minus polynomial equal to 0. And each custom gate will introduce one polynomial. Each like permutation will introduce 2 polynomial. Each lookup will introduce like 4 different polynomial equations. And for custom gate, they won't introduce any extra polynomial. It's just table column, the polynomial for table column. And for lookup, it will introduce 3 different polynomials, like more polynomials. And for permutation, it also need to introduce like two different polynomials. And so this is like at the end of the day, what the prover will give you is that it will interpret the table to some polynomials, and your constraints will be converted to this polynomial identities. Any questions here? Okay. And then like the prover, what the prover need to prove is that I know a bunch of polynomials that satisfy all those relationships. So what prover need to do is that prover need to commit to all the polynomials. Here, like we are using a polynomial commitment scheme called KZG. So because it's the focus for auditor will be more on the how you are writing constraints and how you are writing circuit size. So I won't go into too much detail. But basically, KZG is a polynomial commitment where you can commit to a polynomial and then later prove to the verifier that the polynomial evaluation at a random point is this. So for example, like I'm a prover, I commit to the polynomial fx, and later a verifier want to get this f alpha, the evaluation of f alpha, and without revealing fx, then prover can send this f alpha evaluation to the verifier with some proof, opening proof to prove that this fx opens at f alpha correctly. So this is what polynomial commitment can do. It basically can tell you that a polynomial opens correctly at a random point, and we are using KZG. So this is the biggest difference between the Halo 2 we are using and the initial Zcash team, because they are using some inner product argument for their Halo 2 version, and we use a fork of that version, which we replace this inner product argument with KZG because we want more efficient verifier, and also we want that to be efficiently verified on Ethereum. So the prover need to commit to all those polynomials and later prove that all those polynomials open at random points will be 0. So what prover it's doing is that it will for efficiency, it will linear combine all the polynomial identities using gamma, because it needs to prove that all those polynomial identities vanish over the same set of points. So it can use this gamma to linear combine all those polynomials. Like this is polynomial identities. You use gamma to linear combine all those polynomial relationships and divide by this vanishing argument. So this vanishing argument tell you that it vanish at the rows you selected. It's not, because for example, like so for this polynomial, it won't be always zero. It will only be zero at the row number you give at the table row number. So that's why, like, we need to divide by this vanishing argument. So the prover need to linear combine all those polynomial identities using this gamma, and later open this polynomial at a random point alpha. So this is like how you prove that those openings are correct, and then like this opening are correct will prove that those polynomial identities are equal, and then like it will prove those constraints are satisfied. So this is the whole proving process. Just a quick summary. So you start with some initial program, and your statement will be, I know a secret input of program P such that the output will be 0. So this is your initial program and your initial statement. And next, after writing these constraints, so this constraint will constrain the computation logic in the circuit, and you can use cascade, permutation, and lookup to represent those relationships. And your statement becomes, I know an assignment of the witness table that satisfy all those constraints. And your circuit, those equations will be public. And that's exactly the part that auditors need to audit. Is you need to audit that all those constraints is sound for proving that your computation logic. So like the prover need to prove that I know an assignment for this constraint system. And then like it will be these constraints at the prover side, prover will interpret this table into some polynomial and prove that like certain relationship hold for between those polynomials. So those are like running by the prover after the circuit arithmetization. And finally, the prover need to linear combine all those polynomial identities into one polynomial that vanish over some set. And then like the prover prove that the openings of those polynomials at a random point satisfy those relationships. Because previously, what prover need to prove is that I know a polynomial that satisfies the relationship, but it needs verify to do a bunch of computation for polynomials like divide and but due to the so the relationship of polynomials can be converted to just one random point due to some Zippo lemma, and then you only the prover only need to prove that those polynomials at a random point alpha, the evaluation satisfies this relationship, and that's it. And your proof will only contains the commitment to the polynomials. The prover will commit to the polynomials ahead of time, and the openings, which is the evaluation for those polynomials, and a multi-open proof to prove that the evaluations of those polynomials are correct. And the verifier can check this multi-open proof to know that all the openings are correctly to the committed polynomial, and then it will check this final equation. Like it just check the evaluations have those relationship to know that those polynomials have this relationship, to know that those polynomial relationship holds, to know the constraints are satisfied, to know the program are correct. So that's basically a quick go through for the proving process. Any more questions here? Okay. I think that's pretty much for the Splunk stuff and the prover. Any more questions or?
For the permutation argument, is it necessary that all the elements have to be like in different columns, or can they be in the same column?
They can be in the same column. Like for example, like for one permutation, you just need to specify the max number of columns involved in one permutation argument. For example, one permutation can handle 3 columns, and then you can define arbitrary like values to be equal within the first 3 columns, and that's it. You just need to specify a column relationship.
All right, thank you.
Any other questions? Okay, I think maybe I can hand over to Jordi.
Okay, let me share the screen. Let's move this away. Move presentation here. So can you see my presentation?
Yes.
Yes.
Okay, perfect.
Yep.
Well, so I'm going to explain a little bit the same, but so how we do it in Polygon. We are doing it not using Halo2. We are on this idea of custom gates, at least directly. We're using what we call PIL and what we call create a processor, and then we just run a processor on top of that. So, well, first of all, I'm not going to explain a little bit how Rollup works. I'm going to jump directly to the prover. The prover is the most important, so is what we were very focused on. At the end, we want to have many transactions, many Ethereum transactions. We have an alt state root, and we want to compute a new state root. And we want to prove that actually, when we want to prove that this new state root is computed in the right way without having to compute, so to execute all the transactions again, and we want to do that on chain. Okay, so that's the main idea of the rollups. These transactions are Ethereum transactions with everything in there. So we're talking here to a zkEVM, to a fully compatible zkEVM. That means that all the opcodes are, so it's all the transactions are exactly the same that Ethereum transactions. You can do transfer transactions, you can do deployment transactions, you can do call transactions between one contract to the other. So exactly, so you sign these transactions with MetaMask, and it's exactly the same transactions that you see in Ethereum. Okay, so you need to process. So here, this deterministic program, so this process at the end needs to emulate Ethereum, needs to compute a new state exactly the same way that Ethereum does. Okay, so this is a bit the difficulty of the system. So to do that, well, one first option is to use Circom or this one R1CS kind language, but this is quite unviable and it's quite difficult to do. So the approach that we do is we use mainly PIL. The idea here of PIL is that Circom can be understood as an electronic circuit. So we have a set of gates that you just you put some values at the beginning, and then these gates compute new values, put more gates, values, and at the end you have value. But when you're using PIL here, mainly what you are introducing is this concept of a clock. Is instead of having a big circuit that computes everything linear, unrolled, you can do that with a program. It's like so you can have a state machine. So you can have a small electronics, you have a small gates, and then the output you connect it to the input, and then you are processing. So you have this concept of this state machine. So state machine, at the end, the only thing that you need to define in the state machine is the relationship between one state and the next state. So, and if you have a state machine, then the idea is that if you have a state machines, the idea is that you can build a processor, and then on top of this processor, we are going to run a program that's actually computing, just doing what Ethereum does. So this is the full strategy that we are following. So the idea is that the arithmetization is quite simple, because in the arithmetization, we need to arithmetize only a processor. If you want a small processor with some few instructions, and then it's going to be a program that's going to run on this processor. So the arithmetization in our case is probably quite simple, okay? But in the constraints itself, because most of the logic it's implemented on top of that with many instructions in here, okay? So let's talk a little bit about this arithmetization, how we are doing this arithmetization. It has some similarities with Halo 2, but it has but conceptually is different. Okay, so to do that, well, here I want to start with here is an example. I think that tomorrow we have a plan to do this example, but I'm gonna run to this example fast because I think it's the best way to understand how the arithmetization works is just by doing a simple example. In this case, is Fibonacci series. So, and here in this hello world example, what we want to do is we're working with a finite field. Here, notice that this finite field is a small finite field, it's a 64 bits finite field. So, and this means that all the arithmetization is done in this field, which is very fast to compute. All the witness computation and everything is really fast because we work in these 64 bits. Okay. And in this case, what we want to do is we want to have like a number, and I want to prove that I have two numbers that when I compute the Fibonacci series 1024 times, it gives this number. Okay. If you do it in Circum, that would be quite easy. So you just create these relationships between signals. So you have maybe you have the A0 and A1 signal, and then you just compute the next signal as the addition of the last two ones. Okay, you create these 1024, or in this case is n intermediate signals, and the output of this you just assign to the last one. This is how you would do it in Circum, but here you would have potentially n gates here. So when you are doing, so if we do it the idea is that we can do that in parallel. So the idea is that all these operations that are like the same way that in a we have a state machine. So every state transition you are doing exactly the same. Okay, so this is how we are building with P. So here the idea is that we can have a state machine. In this case, a state machine is of two states. Okay, in this case is the before last and the a last. And here the state transition, the important part of the state transition. So what's the relationship that needs to fulfill between one line and the next line? Okay, or between even the numbers, but just in between two lines. Well, you would do this way. So the before last is the last. Okay, so in the before last in the next line, this is the WX compared to the X is the next line is the last, and the last is just the addition of the last two. Okay, so here what we are doing here is we are defining a state transition here. Okay, so and this is the condition. So how we put that in a polynomial relationship so that we can check that this relationship is computed in parallel. Well, the idea is that we have a polynomial of degree, in this case, to 1023, so 1000 less than 1024. So we have a polynomial, and the idea is that this polynomial can be expressed with 1024 evaluations. So we are representing this polynomial at the evaluations at what we call roots of unity. Roots of unity are just some specific numbers in the field. Actually are the roots of unity. You take this number and you exponentiate that to 1024, then it will give you one for each of them. Okay, so these specific numbers in the field. So when you evaluate the polynomial, so I can define a polynomial here, the a before last, that when at 1 it's equal to 1, at W, which is a specific number, it's 2, at W2 is 3, at W3 is 5, and here this defines a polynomial itself. Okay, so this is the polynomial a before last of x. Okay, so these are not the coefficients of the polynomial, are the evaluations at these specific numbers. Okay, the same thing for a last x. Okay, and here here the expression, you can see the polynomial relationship here. Wx means that, because this is Wx means that this is the next one. So it's like when you're multiplying by W, so you are going to the next value. So a, so this polynomial to AWX is equal to a of last x. Okay, so here is how we express this state machine with these polynomials, and this is the polynomial identities. You know, so we can what we can do here in the system in this problem is we are just committing to a before last, we are committing to a last, and then we prove that these polynomial relationships fulfill after committing so we commit, and then we prove that these polynomials fulfill. Okay, so this is the main idea that we're doing. Here is a kind of a, so here we see the idea of this state machine. Okay, so how we write that in PIL? Well, here in PIL, well, here is before going forward. Here we have a slight problem here. Okay, so this relationship fulfills, but the problem is the last one. So the last one and the first one. So W to 123. This is the root of unity. So if multiplied by W is 124, and this is by definition of root of unity, this is going to be 1. So this is cyclic. So this relationship to here must be equal to here. Okay, so how can I? So I need to modify these relationships just to take in account that this last row with the first row combines, so it fulfills this relationship. So here the trick that what we are doing is we are defining another polynomial. In this case is last x. This is a constant polynomial. This is not a committed polynomial. It's a polynomial that's known by the prover and the verifier. Okay, and it's a polynomial that's 0 in all the roots of unity except the last one, that's 1. Okay, and then we write the PIL this way. So actually this a before last prime, this prime means the next one is equal to the last one. So this must be 0 when its last is 0, because if its last is 1, this is already going to be 0. So I can put any value here. So here you see that I'm with this condition, with this multiplication here, I'm avoiding the last the last row, the connection of the last row to the first row. Okay, the same here. So I'm saying that a last prime must be equal to before last plus a last. So this is the same relationship, but only when its last is 0. Okay, so when its last is 1, then this term is 0. So this will fulfill no matter which values are in a last and a last prime. Okay, here so that's it. So here in this case, I am also defining the output. This is the public output because this is a problem. So I need to define the public output of the circuit. In this case, it's a single public output. In the public output, what I'm saying is that I'm adding this relationship here. I'm saying that when this last is 1, so if it's 0, this will fulfill always. But when this last is 1, a last must be equal to the out 0. Okay, this part here is not part of the constraint. This is just to tell to the prover where they can extract the public value, but it's not here. That's not defined any relationship. It's just a convenience to here. So you can see here that we have the PIL. So here we define it. 2 polynomials, 2 committed polynomials, 1 constant polynomial, and then all these relationships. So what I need to do to define a full circuit here? Well, I need to do 3 things. Okay, first define the PIL. Okay, and then I need to compute the constant polynomials. This is something that I'm going to do once in the setup time. So once per circuit. Okay, at the beginning, and then I will need to create a program that given 2 values, so it computes all the trace, or it computes all these committed polynomials. So actually, it computes all the committed polynomials there. Okay, and with these 3 things, I'm already have I have the polynomials, and then all these 3 things I will plug to a committed a polynomial commitment schema that's going to go after that. But for writing a circuit, the only thing that I need to do is writing these 3 things: the PIL, so that defines the relationship between polynomials; the constant polynomials evaluation, so that's the setup, something that you are evaluating at the beginning of the setup; and the program that actually computes this trace, computes these committed polynomials. Okay, so with this, you see, this is an example, but this is an example. So here, well, you see the example here. You will go to this tomorrow, but here is the idea is that you have the build constants. Okay, here you see that this build constant is quite easy. The only thing that you are doing is that, well, its last is going to be 0 everywhere except when in the last one it is 1. So I'm just setting this here, and here I'm executing. So given an input, I just compute the before last, the last to all the steps. Okay, and just setting this up. Okay, and with this, and that's it. That's the only thing that I need. With this, I can already connect to PiloStark. PiloStark is the backend, the cryptographic schema that actually do all this polynomial commitment, and everything is translated automatically in PiloStark. Okay, so This is PIL. You see, it's quite easy. You define committed polynomials or constant polynomials, and then you define the relationship of these polynomials. Okay, but you can do more things in PIL. You can define some special relationships of the polynomial that you can look at the end. This is going to be converted to a basic committed named polynomials. But you can do, for example, a permutation check. What means in a permutation check? Permutation check means that you have two polynomials, and you say that, well, this polynomial is exactly the same that this, but the only thing is that switching. So the permutation is different, okay? But all the values here, and the values here are exactly the same. So how can I define that in PIL? Well, I'm just saying that A is B. Okay, so that's as easy as that. So I can commit to two polynomials, and then I just can prove that all this. So when I generate a proof, what I would prove is that these polynomials are, one is the permutation of the other. Okay, I can do a permutation check, but in multi-columns. For example, I can here you see, for example, A1 and A2 must be so this must be equal to B1 and B2. Okay, but in different order, and with only some selectors, only in the columns that where select A is 1. So only in these rows, on the rows that selected here, I want that this being here. Okay, so in this case is the 3 is here, the 2 is here, the 4 is here, and the 1 is here. And no matter what are the other values that are here. So this is what I want to enforce, that this relationship follows. Okay, and how you write that in PIL? Well, you write this way. So selector A, here you have the columns that you want, and is selector B, B1 and B2. So defining these polynomials, so defining these relationships in PIL is very straightforward, very easy. You have all these relationships here. Okay, so it's in it's a specific language. It's a language that's built for that, and all the zkEVM, you can read and you can see all the PILs. So all the PIL files are in the VM. Okay, what else you can do? You can do BlockUps. Okay, for example, you can see that all the values in A must be in B. Maybe it's possible that there are some values here that are repeated, or some values in B that are not in A. Okay, but this is just an inclusion, set inclusion. It's a BlockUp. Okay, so I can do these polynomials, and here what I'm saying is A in B instead of is B. Okay, I can do also with multi-columns and with selectors the same way. So here is the 3 must be included here. You see here, for example, that 3 is 2 times, but this is correct because it's a BlockUp. The 4 is here, and the 1 is here. Here I have the 2 that we have no representation, but this is okay. And you can have a selector in the left and in the right, so in the inclusion and the no inclusions. Okay. So what else you can do in PIL? In PIL you can do the connections. Okay, so this is what you want to, for example, in this column, I want to force that the first evaluation, the fourth evaluation, the fifth, and the sixth are exactly the same. Or I want to force that the second evaluation and the seventh evaluation are exactly the same. So how do I do that? Well, here I define a polynomial. In general, it's going to be a constant polynomial, but can be anything, but it's going to be a constant polynomial that actually is the identity polynomial, but with these permutations. Okay, for example, the first, the third, the first, fourth, fifth, and sixth also is 1, W3 or W4, W5. What I'm doing is I'm doing a rotation. Okay, so I'm just putting this, but in a different, in a different rotation. It's W5, 1, W3, W4. So it's a cycle. It's a cycle. So what I'm saying here with defining this cycle, it's that these evaluations must be the same. Okay, the same with the second and the seventh. So the W and W6 here is W6 W. Just do the rotation. Okay, and the same W2 W7 W7 W2. Okay, and I can do that also with multiple columns. So I want to connect. So I want to, in this case, I want to connect the first with the third. So how I do that? I'm defining. Well, in this case, is in the case of having one identity polynomial, I have 3 identity polynomials. Is this K1 this and K2 this, and then I'm switching. For example, this number 5 and this number 5. So I'm just switching. This would be the K2W, and this is the K1W2. But I'm just switching one by the other. In this case, it's doing this cycle of rotation. Okay. How do I write that in PIL? What I'm just saying in this case is A connects S, or if I have multiple columns, I'm just saying that A1, A2, A3 connect with S1, so according to S1, S2, and S3. So I'm forcing that this is a copy constraints. This is copy constraints. Okay. For the people that know Splunk, actually you can write easily Splunk in PIL. So in this case, you define well the committed polynomials ABC of Splunk. You have the SA, SB, SC. This is the connection, the copy constraints polynomial. Then you have the Splunk gate. In this Q left, Q right, Q multiplication, Q output, and Q constant. Okay. And then I'm defining here what this is the relationship that these polynomials must fulfill. Okay. And then here you have the connect. A, B, and C is connects to that. In this case, I am also defining a public input. Okay. That's in A0. And I'm defining the constant L1, which is a polynomial that's 1 in the first and 0 to all the remaining rows. And then I'm just saying that at L1, I'm forcing that A is the public input. So this is an example of Splunk with one public input. Okay. But you can see that you can write any kind of Splunk. So Splunk is just an example of PIL. Okay. But okay, but all that that's great. But how you write a processor? Okay, because this is okay. This is very good because this is a state machine. But actually, how you write the processor? Okay, so let's create a processor for this, because this is a simplified version of the processor that we have, but it's very, very, very simple. So conceptually, it's exactly the same that we are doing. Okay. So the idea of a processor is, see, we have so in the processor actually we have a set of registers. In this case, we have registers A, B, C, D, and E. These are going to be committed polynomials, the state of each register. And then we need to define, so and here we need, in each step, we need to compute a prime, B prime, so the register will evolve. For example, if I'm doing a move between A and B, so I need to copy A to B in an instruction. And in each step, I'm executing an instruction. Okay, an instruction in our case is defined by a set of multiple, so it's a set of multiple polynomials. Okay, here an instruction is the instruction here in this polynomials is the instruction that I am executing. Okay, so there's going to be a polynomial that is saying which instruction I'm executing at each clock, so at each row in this case. Okay, so and the instruction in our case, for example, can be in A, in B, in C, in D, in E, a constant, a free in, all these things that you see in white. This is part of the instruction. Okay, so the instruction and every instruction in A can be 0 or 1, in B can be 0 or 1 or a number. Okay, const can be, so you can understand this as a single polynomial. Okay, and this is how I'm defining the relationship. So how I'm computing A prime, B prime. So I'm computing the next step. Okay, so in this case, well, I'm defining here intermediate polynomial. In this case, you see PolOp. This is just a calculus. So I'm just taking some polynomials and computing an intermediate value. And in this case, what I'm doing here, what OP is, I'm just selecting somehow some of the registers. Okay, actually, I'm adding the registers. So imagine that in A is 1, and in B, in C, in D, in E, everything is 0. Okay, so here is A times in 1, B times in B. So in this case, in 1 is going to be 1, so OP is going to be 8, and the remaining are going to be 0. Okay, I can also, const is also part of the instruction. Okay, well, all const is also part of the instruction. So I can, for example, op can be a specific value here. Okay. And in this op, then with this op, what I'm doing is I'm assigning to A prime. So how I'm computing A prime? Well, if set A, if the instruction have the set A bit set to 1, then this is going to be op minus A plus A. So this is going to be op. So I'm going to set the value of op to A. Okay. If set A is 0, then I'm just going to keep the last value of A. Okay, so a move instruction will be an instruction where, for example, if I want to move from A to B, then in A is going to be 1, set B is going to be 1, and in B, in C, in D, in E, and set A, set B, set C, set D, and set D is going to be 0. Okay, so set B is going to be 1, so I'm going to just move the value of A. I'm going to put to B. This is going to be a move from A to B. If I want to execute, for example, an immediate value, imagine that I want to put a 4 in register C. Okay, here const, so in A, in B, in C, in D is going to be 0. Okay, const is going to be a number 4. Okay, this is the immediate value. Okay, so OP is going to be the constant. Is going to be this constant value, and then I'm going to put the set C is going to be 1, and the others are going to be 0. So I'm going to put a 4 in the number C. Okay, you see here that you have registers, and here you have a processor that have registers, and in this case, it's executing only instructions that are doing moves. Okay, so but I can move any value of any register to any value of any other register. Okay, and I can also have this constant, these immediate values. Okay, here I have another important polynomial is the freeing. So there are some instructions that it's going to allow us to put any value to OP. Okay, this is because in general this processor is not going to really compute anything. Actually, what's going to do is going to verify things. Okay, so it's quite typical and it's quite useful. For example, you do a division, then what you do is you put the result of the division, and then you are checking that the result that you put in the division times the quotient is equal to the dividend. Okay, and then you will have another instruction that's actually checking this operation between registers. Okay, so it's quite common, not all of them. So this is the in freeing. Okay, but some instructions, and sometimes it's interesting to have this to allow the system to introduce a specific value. Probably, well, because you're probably going to check this value later on. Okay, but this is well, here the other thing is sometimes you want to have conditional jumps. I'm not going to enter in detail here, but the idea is that I can have for example, I can have OP. I can check if this is 0 or it's not 0, and according if it's 0, it's not 0. I have a program counter. Okay, that actually is saying which instruction of the program should I be running, and then in general, if it's not a jump, I'm going to just go to the next one, next instruction. But if it's if actually the jump happens, then I'm going to jump to an address. An address, this maybe for example, is part of the instruction. Okay, so here, well, here is the E0, and at the end is the PC's jump. If it's jump, then I'm going to the address minus PC plus ink plus PC plus ink. So I'm going to the address, and if it's jump is 0, then I'm going to PC plus ink. Ink is 1. Is the next instruction. Okay, so with this you have a processor, but the thing is that here we have a problem because we commit to the instructions. Okay, so the instructions are committed polynomials, so I can execute any instruction that I want, but which program I'm running. So here I'm just I can set up instructions. If I put a specific instruction, the processor is going to execute that instruction. It cannot execute anything else, just that instruction. But I could put why in the first clock I execute a jump, in the second I'm executing an addition, or in the third I'm executing a move, and not something else. Okay, so here is how I link. Okay, and the idea is I can have a ROM. A ROM is a constant polynomial. Actually, it's the program that I'm running. This is constant. Okay, and here you will have the instruction. You can read here. This is going to be a set of polynomials. In this case, add, jump. This is going to be all the polynomials in A, in B, in C, set A, set B, set C, set D. So here are all the polynomials that compose the instruction itself. Okay, and here the only thing that I'm adding an extra polynomial, which is the row line. Okay, so and this is constant. Okay, so I can create a program, a specific program. Okay, that's going to start from the beginning, and this is a program that I want to run to my processor. Okay, here see the instruction is a set of polynomials. Okay, but have a specific polynomial, that's the line. Okay, and in my trace, so in my main state machine, okay, I will have the instruction that I'm executing. This is a committed, or this is a committed polynomial. So this is here I can put whatever I want. I can execute in the first line a net and a jump or whatever. Okay, and here I have the program counter. The program counter is the line that I supposed to be executing. So if I start from the 0, that means that the program counter must be 0. If it's because it's an add, then this program counter must be a 1. In this case, a jump to 5, that means that the program counter I jump and this I need to execute the line 5. The 5 is the mul, so I'm executing a mul here. Okay. So how do I check? How can I force that I'm executing this specific program? Well, I'm just doing a BlockUp. Okay, I'm just doing a BlockUp of the program counter, and all the instructions must be included in the program line and these instructions. That means that if because there is only one line 1, so if the program counter is 1, that means that all the instruction must be exactly the instruction that's in the line 1. Okay, and with this way, so having the constant, so the program itself, what we call it the ROM, okay, the program that we are executing, and we have the instructions, the committed instructions, that actually the instruction that I want to execute is when I'm forcing that I'm executing that program. Okay, but the program is fixed, it's a ROM, so I cannot change, it's hard-coded, it's a constant polynomial. The prover already know the ROM, okay, but how you execute the program is going to change. Maybe sometimes it's going to be an if that's going to be one way and the other way. So the instruction that I'm executing at the specific clock is going to be different. Okay, so that's why I have this instruction that's in the main, the instruction that it's a committed, it changed for every iteration, and I have the instruction that's executed, so that the instruction on the program, on the ROM. Okay, so this is changes, and then with this simple BlockUp, I'm just forcing that I'm executing this program. Okay, so you see here, this is the basics, but this is, you see that with PIL, I can define easily a processor. Okay, we have registers, we have a program counter, we have a conditional jumps. Here, I can have instructions, and well, I can add things on top of that. And then, but then at the end, I have a program, and I'm executing a program. Okay, so now I need to just get this, do this processor richer. Okay, just to build the zkEVM. So for example, I want to add memory to this processor. How do I do memory? Okay, so the idea is that I'm going to have instructions that are reads and writes. Okay, so in this case, for example, in the clock 1, maybe I'm executing a write instruction to memory to the address 5 and the value 2. Okay, and I'm doing in the 2, I'm doing a write at address 3 and 8. Okay, and I will have a set, this program will have a set of reads and writes. Okay, when I'm reading, I'm just putting the value. But I want to verify that these reads and writes are okay, correct according to memory. So I'm just reading. If I write a 3 in the position 4, the next time that I'm reading it, I need to read 3. No, I cannot read a 5. Okay, so that's the thing that I want to check. So in order to check that all these reads and writes are okay, what I'm doing is I'm just creating another state machine. This is a state machine. I'm just putting all the instructions, but ordered by address instead of ordering by the count. I'm just ordering by address and by the clock number, if you want the count. Okay, so because all these addresses are packed, then I can do these reads and writes in a single register. So here in the memory state machine, I can just put the conditions first to force that this the address is sorted, and so I'm just forcing that in this state machine is sorted, and also that the reads and writes are done in the right way. So if I'm putting a write of an 8, then when I'm reading an 8, and I'm just at the end is I'm just reading the value. I'm just changing the value of this register when I'm doing a write. Okay, and then here with a single permutation check. Okay, so I'm just permutation check, of course, selecting only the reads, the memory operations, so the ones that you see here. Okay, so only that one. I'm just doing this permutation check with the memory operations here. So with this simple permutation check, you can prove, so you can have a ready memory. Okay, so we have a state machine, we call it memory, that's actually doing this, and then it's a link between the main state machine and the memory state machine in order to force to have memory. Okay. We have, for example, another state machine that's actually computing arithmetic state machines. For example, it's doing multiplications of 256 digits, okay, which is a complex thing. So we have a state machine, but it's very specialized just for building multiplications of 256 bits, or if you want arithmetic operations on 256 bits. Okay, and the idea is that in the main state machine we just want to prove, so we put A, B, C, D, and O. Well, in this case, OP. Okay, so we want to force, for example, we want to force that, for example, A times B plus C equals D 2 times 256 plus OP. Okay, so there is a 256 bits relationship that needs to be fulfilled here. I want to force that. So how can I force that this relationship here is okay? Well, what I'm doing is I'm computing. I have this arithmetic state machine where I compute all the operations that I'm using, the total operations that I'm doing in the main state machine, and with a single, in this case, a permutation check. Okay, I'm just checking that all the operations that I am doing here in the main state machine are also done here in the arithmetic state machine. It's a permutation check or a lookup. Actually, we started with a lookup and now it's a permutation check because it's easy. But yeah, okay. But that's so. Here is the other idea of the system. We have a secondary state machines. So we have other like coprocessors that are doing specific operations. And in the main state machine, we are just connecting via lookup or via permutation check to these for doing these operations. Okay. So and all these relationships this is defined in PIL. Okay. But here, so what's the system? So what's the zkEVM? So what's the zkEVM? What's composed of? Okay. So we have the processor. Okay. So we have the main processor. We have the RAM. Okay. We already see this RAM. This RAM in the EVM has some specific things. For example, some pagination, some context and things just to work. For example, that works well in the zkEVM, because when you're just doing, when the smart contract is calling another smart contract, you have like a new RAM. So in this case, you have a new context, and so we have this memory paginate in that. And then also we have like a super state machine. It's like another state machine to handle all this misalignment. The problem of the EVM is that's 256 words, but the memory is byte aligned. So you can read something that's between words, just you can start at position 7 and go until position 7 plus 32, and then you need to read maybe from memory in the different places. So to do these joins and to do these separations for the reads and writes of memory, we have a special state machine that we call aligned state machine. It's a very small state machine, but it's specific for for optimizing this part of the EVM. We have the ROM. We already talked about the ROM. This ROM is actually it's Ethereum, so it's implemented all the Ethereum in the ROM. We have a storage. Okay, so the storage that we're using here is a sparse Merkle tree, very optimized for the Goldilocks field. Okay, but at the end, this sparse Merkle tree is key value. Okay, so it's a key value database that you can hash for a given set of key value. You have a hash, and then you can do reads or writes to this storage. Actually, this storage is the way it's implemented is another processor, same way that we have the main processor, we have this storage processor, and in this processor we can do the you can set to 0, and sometimes in the sparse Merkle tree there are some different conditions and some logic of the sparse Merkle tree. So this is done like another program that's doing all these operations, but the technique is exactly the same that I explained in this state machine. What else we have? We have an important state machine is the binary. In this binary, we are solving all the instructions that, for example, for doing add, sup, less than, sign less than, equal, answer, and XORs. Okay, this is for the normal operations in the EVM. So these operations are doing this. So this state machine is doing these operations on the 256 bits. Okay, so in the main state machine, when you need to execute XOR of code, mainly it's gonna do is it's gonna call this binary state machine. Okay, The arithmetic state machine, I already explained it a little bit how it works, but the idea is that you can do 256 bits operations. Okay, so we have one operation every 32 clocks, and is doing their specific 256 operation. Okay, and here in this state machine, it's not only doing this basic 256 state operation, it's also doing some ECDSA doubling, addition and doubling operations. So to check the ECDSA of the transactions actually is well, it's a program in the main, but is using this specific function for doing all these elliptic curve operations as a special instructions of the arithmetic state machine. Okay. And then we have the ketchup, okay, the ketchup and all the hashes, but the ketchup at the end is well, we have a specific state machine that computes ketchups. It's not only ketchups, it's ketchups and all the paddings and so on. Okay. Okay, so this is all the hashes are some specific state machines that are quite well, are probably maybe a little bit complex, but they are handling all these paddings with for ketchup or paddings. So for example, all the codes, all the source code, we are hashing it with Poseidon because it's much more optimal. Okay, but we need to implement ketchup for the CDSA for the CDSA verification, and also because the EVM also hosts ketchup. Okay. So this is a little bit the processor. So you see that the processor, it has some basic instructions, okay, but then there is the real program. That's the program that actually is running on top of this processor, okay. And but this is not the arithmetization anymore. So you see that the arithmetization here is quite simple. Is the constraints are defined in pill. You can the pill is divided in very concrete state machines, and each state machine is not. Some of them are a little bit complex, but there is no state machine that's bigger than 100 or 200 lines of code. Okay, so it's quite easy to check, to validate, to audit, and to check that all these constraints, these polynomial identities are okay. Okay, so this is the idea of the one of the parts of the auditing part. Okay, from the ROM perspective here. Okay, so now it's a program. Okay, so here is it's the hardware design, so it's build design. Okay, and then we have like another domain that's the program design. Of course, you need to understand how the processor works, because at the end you are programming in assembly, but you see a program. Okay, and the best thing here is just to take a look and how this program looks like. Okay, so this is the program. Okay, and I want to explain a little bit what's the structure of this assembly. Okay, so you can just go here and see a little bit what we see. Okay, so in the first part, what we see here is, for example, we have some places that there is an arrow. Okay, and here it's at the left is a selection. In general, it's an addition. Here is just guess plus b. So here in general is you are selecting something and then you are assigning to something. Okay, so well, let me just have some example here. Let me just here is. Okay, so here, for example, in this case is the move A to B. So what I'm doing is I'm selecting A and I'm setting to B. So when I have this instruction in assembly, what it means is that I'm going from A to B. Here, for example, this is the immediate value. I'm just putting a 0 to A and B. I can put here 3 to A and B. Here, and in the same instruction, this means that set A and set B are 1. So I can this processor allows me to set 2 registers at a time, or setting a register at a time. So I can do this with this way, okay? Or I can, for example, do an addition. This is it's not a 256-bit addition, it's a field addition, but I'm just adding A and B and just setting the value, the result to A, okay? When in the left side, I see $, that means that's a free input, okay? But a free input, but okay, but it's a free input, but so the system allows me to put anything in there, but what I should put here in there. So in order to indicate to the executor, the program that's executing this, executing this program, what value needs to put. Here I have like a sub language, that's this dollar, and here, for example, here I'm putting part of the transaction as an example. I can put maybe an operation. I can put maybe 5 plus A, or I can put, so here I have a sub language here just to tell to the executor what I need to put. But here actually I can put anything in here. Okay. Sometimes there is this dollar without these brackets. And that means that's implicit. So in this case, for example, I am executing a memory load, so I don't need to tell. So if I'm executing a memory load, what I'm going to do is I'm just here. The executor already knows that's going to put the value that's stored in this position. So there is these implicit values. So when there is no dollar, this means that's an implicit value here. Okay. Okay. And here in the left, it's a column. Sometimes I'm gonna have the instruction itself. Here I can have a add it, or less than, or maybe a jump, or envelope. Here I have the actual instruction that I'm executing or checking or validating here. I can have here labels just for the jumps. I can have variables. I have two kinds of variables: global variables that are in like system variables, and then I have variables that are context specific. So can define, and this is save it in a specific place in the memory for context on that. Okay, and there is something that this is not an instruction itself. It's just it's just an indicator to the executor to do something, to do some commands in there. There are things that you don't need to execute anything in the program, but you need to tell the executor maybe to increment a variable, or to maybe to lock something. For example, all the traces are done via this way. So every time that you do you finish an opcode, you are just notifying the executor that this opcode is executed. So the executor can do other things in there. Okay, but here you see this is the example of the language. If you go to the you can run to the ROM, and well, here for example you have all the opcodes implemented. Okay, actually it's the full the system is already finished, so you can check this. For example, this is the RLP of the transactions. So here you come how you process the transactions. Okay, so okay, you can have here for example the process of the transactions itself. So, well, you can just run to the output. See, this is all the IBM. This is like if you are reading Geth that you are that's running the Ethereum. Here you can read exactly the same. Okay, and actually this is well, here have just for some, there are some instructions that you can do in the assembly. You can do memory load, memory store, storage load, storage store. You can do all the hash management, your hash Ketchak and hash Poseidon, the two hashes that you have in the system for managing hashes. You have the arithmetic, you have an assert if you want to just invalidate the proof or something like that. You have the memory align things. You have all these add sub, so all these binary operations that you have one instruction for each binary operation that you have there, and that's it. Okay, so this is the arithmetization. This is how we are building the zkEVM. Of course, the processor has. Well, actually, it has 5 registers. It has more registers. These registers actually are 256 bits registers. That means that are really 8 polynomials of the Goldilocks, and each polynomial is a chunk of 32 bits. Okay, so this is 8 times 5 registers here, and we have a bunch. Well, you can see the pill, and you have all the instructions there. So it's you have some other special registers for gas management, for memory management, but there are 3 or 4 more. The gas and yeah, so that's very much so, but it's not much more than that. Okay, so it's a little bit that, but you can, well, when you go deep, you can go to the details, but it's very much this this is the instruction. So the main state machine. In the other side, you have the ROM. Okay, what else? Yeah, Yeah, okay. Once we finish that, at the end, we have a set of polynomials, okay? And this is automatically done, okay? But actually what we do here, okay? So here we are using a polynomial commitment schema, very similar to what Scroll is doing, but instead of using the Cape commitment, here we are using a Fry-like commitment. So Fry is just for, it's not really a polynomial schema, but can be converted easily to a opening polynomial schema for that. Okay. Well, yeah, just coming to the polynomials. Actually, this is our 3 steps actually, and then just get the values in each step, and then we just do the openings. Okay, so you just evaluate a specific value, and then you just verify that these polynomial relationships are okay. Okay, so this is the typical of the polynomial equivalent. Okay, of course via Shamir. And then the other thing, so this is, we have a proof, okay? So this is a proof, actually is a Stark, it's actually is around 600 polynomials or something like that. We're reducing it a little bit right now, but it's around 600 polynomials and of 2 to the 23, degree of 2 to the 23. This is the main proof, okay? And each proof here, it has a, so it validates a batch, okay? Actually, in each proof for 2 to the 23 is more or less, it's an average, but more or less is about 4 million gas, equivalent to 4 million gas Ethereum here. Okay, so actually this is the more updated stroke of the proof. So here, what we are doing is for each batch, we are creating a proof. This proof is a big proof. It's a proof that's just here only it's because this proof needs to go fast. This is just a blow-up factor of 2 only, so it's 128 queries. So this proof is quite big. Okay, it's a big proof for itself, and verifying this is costly. So here we have a compressor circuit. We call it C12A. Okay, but this is actually converting this proof to another proof that's just much smaller and just much manageable. So instead of 128 queries, here is just 64 queries with much less polynomials each one. Okay, and then this and here we have like this is like an adapter. We have another circuit. We call it a recursive one that actually converts to a proof of a batch to a proof of a segment. That's a segment of just one batch. Okay, segment of a blockchain. Okay, and then actually we have a recursive circuit that takes 2 segments, no matter if it's of 1 or if it's of 10, and they just join together to a new proof segment of both. It adds 2 segments. It needs to be consecutive segments, but I can, for example, aggregate the proof of that proof from 3 to 6 with the one that proved from 7 to 18. And I can join them together and I just create a new segment. Okay, and this is iterable, so I can do this as many times as I want. So again, I can generate a proof of 30 batches or 1,000 batches or 1 million batches. It's just a matter of just aggregating it. Okay, so at the end, this is, so we have this. So at the end, we have a single proof, and then here this we have another circuit that's mainly commercial Stark, but instead of we're using the Goldilocks as the Poseidon, as the hash function, is using the Poseidon, but for the BN 128. Okay, and we have a final circuit that's a circum circuit, a normal regular circum circuit that generates a Splunk proof, Splunk or Gross16, a Gross16 proof, and this is actually what's validated in the blockchain. Okay. So this is the schema for the recursion schema, so the aggregation schema for the system. Actually, it's this is not in the testnet yet. Let's see if maybe next week we can put that in testnet. Let's see if everything works. We are testing it internally at this point. So at this point in the current in the testnet is just validating each batch, one proof per batch. Okay, but now in the next week we will have this on this aggregated proof system. Okay, and yeah, that's very much the thing. So proof cost, but this is more technical things. Right now we are getting these very low, so we are 8 minutes, but with GPUs and so on, I think we can be just below 5 minutes for sure there. So we are we are doing very good work in this. And yeah, here is for testing this is important. So we are running all the Ethereum test suites. So we are getting all the tests and we are passing all the Ethereum tests or okay. And there are things, so actually we are implementing almost everything. Things that we are not implementing in this first version are gonna be the SHA-256, Blake, pairings. These are the precompiled smart contracts, and mainly that's it. Mainly that's all the remaining things, all the opcodes and everything else is implemented. Okay, there are some slight difference, but it's just very few things. Normal users should not notice at all this. Okay, and yeah, here is all the repos just for you to take a look. It's you can go at 0x Polygon Hermez. Okay, and here you can check all the proofs. Okay, so that's very much my presentation. Of course, there is a testnet. So if you want to test, also testnet is here. I'm sure you already know, but it's you can take a look how the system works in here. Okay, so that's very much it. There is not October 30. It's November or something, but yeah, that's my presentation. I don't know if there are questions.
Or processors, like for example the memory one and the main one. I'm assuming that you basically need to recommit the table if you're doing it via lookups, right? Because like the order of the things might not be the same.
Yeah, so there is two state machines. There are the polynomials in one state machine, another polynomial in the other state machine, and then we are yeah, in general, so we have two polynomials and then we just check the relationship, but you know, polynomials in one state machine are ones and polynomials in the other state machines are others. They are not shared, they are just compared. So yeah, that means that sometimes we especially the results, we have these twice. We have two polynomials, one in the main state machine and the other in the main state machine. In general, are the registers. For example, for the arithmetic state machine, the polynomials are the registers, but you need to have some kind of a replica in the arithmetic state machine. In the arithmetic state machine, you need to output, so you need to create we call it the latch, okay, because this is the results that's generating the arithmetic state machine. The end is generating statements saying this number times this number plus this number is equal to this number. Okay, so and these four registers are A, B, and C and D in the main state machine, and then you do the lookup or permutation check between one table, one state machine, and the other state machine.
Okay, makes sense. Thank you. And the other thing was regarding what you basically said at the end with the segment proofs and the recursion stuff, which is what I'm assuming. Maybe I'm wrong, but is that you basically want to lose the link in between a proof per block, basically, so that you can constantly feed whatever prover you have. And it might be getting things in between blocks, or it might be verifying, proving, like whatever it is. You can just throw stuff at him, right?
So we are not proving blocks, we are proving segments, which is a set of blocks. A segment can be of one block, okay? But in general, it's going to be a segment between batch or block 25 and block 63. And I'm just
exactly.
Proving, yeah.
So kind of my point here is, do you need in between those segments, like how is it possible to not need to commit data of the state in between one segment and the other? So for example, if you are in one block and you have done some reads and some writes, and in the next one you need to have this information available. So how do you manage that?
The idea is that, the sequencer is just putting transactions in the layer one, okay? And these transactions are deterministically generate the state, okay? So anybody, so at the end, everybody can deterministically, if you have a state and you have a set of transactions of maybe of 10 batches, you deterministically know what's the next state. You can compute, anybody can compute. The only thing that you are doing with the proof is you are putting these New state, explicit. You are putting this new state on chain. And when it's on chain, then is when you, for example, you can withdraw. Because the chain already knows that this is the real state. That's a big point. But before that, the transactions are already final. So the state and the state is known. You need to compute it, but it can be computed. Okay, so anybody can compute because it's on chain.
Okay.
Okay.
Okay. Thank you.
And the interesting thing here is that, and this is important, all the transactions are deterministically executed. Okay, and we have also this concept of forced transactions. So any user, so in general, the user will send the transactions to a sequencer. But if the sequencer, for example, is censoring the transactions of a user, the user can always send these transactions on chain. They will have to pay the gas, but they will put the on chain. And then the sequencer will be forced to include these transactions. If not, he will not be able to sequence any other batch. So the sequencer will have to put those transactions, and these transactions can be any random string. So it can be anything wrong. Okay, so it can be anything that you can imagine there. And for example, it can be a transaction with an invalid nonce, or it can be a transaction with with an invalid signature, or with maybe with a loop of ketchups that doesn't fit in a proof. Okay, so and here the prover needs to the prover guarantees that it's going to be possible always to compute the proof, no matter what's the transaction that you are inserting there.
Okay.
And this is probably one of the difficult things, but this is guaranteed in our system, at least theoretically.
Okay. Thank you, Jordi.
More questions?
You said about gas calculations. So does it mean that your EVM also calculate gas costs of the execution? And
exactly.
Exactly
the same that Ethereum.
Why do you need this if you don't actually charge?
We need this because we want to be 100% compatible with Ethereum, and program user, so adapt, should not notice any difference between deploying or using a smart contract in the zkEVM or deploying a smart contract in layer 1. Except
so you need this to make the gas opcode work properly, right? Yes. I mean, the program should. Well,
the gas code and the works at everything exactly the same. Here, it's interesting to notice here that the gas, the cost of the EVM and the cost of the gas cost of the EVM, the zkEVM and the EVM, is not that different. There are some exceptions. Sketchup is one of those, and so, but it's not that bad. Okay, so that means that the deviations. So in normal use cases, users should not have any issue on that. And if you go to extreme cases, well, maybe there is some transaction that maybe it's not going to be processed in the zkEVM, but it's going to be very extreme cases. This is a loop of ketchups or something that a loop of. But even it's going to be difficult. It could be a loop of maybe arithmetic operations, but it's difficult to get this. So you need to be very good at defining these and setting and constructing these operations, because they are very special. Most of the operations are running right now. For example, we deploy Uniswap v3 without recompiling anything, runs perfectly. Just throw the compiled smart contract, same that and it's running. And Uniswap v3, for example, is a quite complex set of smart contracts. Here,
okay.
Or Truffle or any or Hard Hat or any other tooling, you have how to use MetaMask, and you use anything, and everything works. You don't need to worry about. I think this is nice.
No, I mean, you are trying to preserve compatibility at high extents, and Ethereum itself preserves it, right? Because every hard fork can break compatibility and could, in theory, affect old contracts, right?
Yeah,
I mean,
we will follow so a hard fork. So we will follow hard forks of Ethereum somehow. But we need to see this. Is you are talking on something maybe it's going to take a while. I think the first is just being quite 100% compatible and meaning and having a warranty that the system is not going to change for a while. In general, hard forks of Ethereum, they don't use. They are trying. So they don't use to break too much, okay? Because the tooling would not working. So we need to see case by case and see what's adding and see if this is included or not included. I believe that we need to follow a little bit, but this is something that we need to manage. But in any case, at some point, what's clear, and this is important to know, is that at some point the EVM will have the warranty that the EVM is going to be frozen, and at that point, it's going to be also the time to freeze the rollups. But maybe it's going to take some years.
Jordi, if I can ask, one of the cases that I believe that can be a problem, at least is for us, is instructions like Xcode size or Xcode hash, which force you to copy a lot of code to the memory, well, from the memory, and then count it, hash it, do a bunch of stuff, and it's pretty cheap.
In our case, for this, for example, what we are doing is when you are deploying the smart contract, we just, at that point, very easy what's the hash and the size, and then we store that on the storage.
Okay,
so
okay.
This is quite, in those cases, is quite relatively fast. There are some things read code itself, but we are using this. So for storing the code, we are not using Ketchup. We are using this Poseidon. So it's quite fast. It's quite fast for loading the code and executing, and this is quite fast. Here, well, any question? Just I don't know where. Maybe probably Grace or somebody will send some link. But here, me and all the team is open to any questions you may have. Okay, we continue. I think we continue sessions tomorrow.